Hello guys, and welcome to my channel. In this video I'm going to show you how to derive maximum bending moment for a separated beam with a uniformly distributed load. So this is the beam that we have, and we've got point A and B separated with L meters, and that is it. So as you can see from this diagram, taking the loads and directions from point A to B, you can actually see that direction at A will be equal to direction at B since the load is uniformly distributed. So we can say that direction at A will be equal to direction at B. Okay, so as you can see also, and we know that upward forces will be equal to downward forces. So for upward forces, we got direction direction at A and direction at B. So it will be direction at A and at direction at B will be equal to, that load is expressed in Newton per meter. So we're going to multiply that weight multiplied by the length L. Okay, so it's now a force. So since RA is equals to RB, we're going to express these two in terms of A. So it will be 2RA will be equal to WL. So it leaves RA will be equal to WL over 2. Okay, so this is the reaction at A, which is equal to reaction at B. At equilibrium, all moments about X must be equal to 0. So if we're going to sum all moments about X, they must be equal to 0. And at equilibrium, that is what we have, and we're going to use these signs for all anti-clockwise moments will take a positive sign, and all clockwise will take a negative. So taking those at this point, let's just assume that this is a new pivot. Mx will take a positive sign because it is going anti-clockwise. So we're going to write it here, positive mx, right? And what else do we have here? We've got a load here. It will be going in this direction, so it will be in anti-clockwise direction, taking this as a pivot. So what do we have here? It will take a positive sign, and we're going to add it here, and this weight now is acting over x meters, so it will be wx. But now we know that the center of gravity, it will be at x over 2, so it will be at x over 2, and we also have a direction that is going upward. So the direction, if it is going upward at this pivot, it will take a negative sign, so we're going to subtract it with RA. But we know that RA is equal to WL over 2, which we've just solved up, so it will be WL over 2, and it is acting at x meters, so we're going to multiply by x here. So this is what we have, and we know that from bending equations that mx is equal to, let me write it here, it will be mx is equal to ei squared y over dx squared. Okay, so as we said that summation of all moments about x must be equal to 0, we're going to equal this one to 0, which will be equal to ei d squared y over dx squared. So here I'm going to make mx as the subject of the formula, so it will be mx will be equal to WLX over 2, and subtract WX squared over 2. This is what we have. So it will be equal to ei squared y over dx squared. Okay, so this can be factorized so as to reduce the powers of y and x. So if we are going to factorize here, we get ei is a constant, and the square y, it will be dy dx, and we're going to equate it here. If we are going to factorize for x, we have WL over 2, factorizing x with x squared over 2, and we are subtracting this, we are factorizing x squared. Factorizing x squared, we've got x cubed over 3 and a constant c1. So this is what I have. So I'm going to number my questions so that there will be no confusion, and taking this as question 1, this one is equation 2. Okay, so dy dx, this is a slope, so it will be the angle of deflection, and on the upcoming videos I'm going to show you how to calculate and derive from the angle of deflection. And if we can reduce this also by integration, we come to a point whereby dy dx, if we reduce it, will be y, will be equal to, if we're going to integrate here with wl over 2 by 2, and we're going to integrate for x squared, x cubed 3 here, and we're going to subtract w 2 by 3, it will be 6, and here x to the power 4 over 4, and here our constant will be x. We're going to add x c1 and c2, and this will be the third equation. So if we're going to calculate for the bending moment, a bending moment if you can go back to our diagram, when this beam is subjected to a load, it will deflect in this manner. Okay, so the maximum bending will occur at half length of this length from point A to B, so it will act at L over 2. This will be L over 2. Okay, so this is the point where we experience the maximum bending moment of this beam. So from the equations that we have, this is mx, we are going to set some conditions that m for maximum bending moment, m will be equal to mx at x is equals to L over 2. Okay, so we're going here and substitute for x, we're going to put L over 2. So m now, for mx, we're going to put m will be equal to WL x over 2, WL x over 2, and subtracting WX squared over 2. Okay, and here it is equated to EID squared y over dx squared, which is equal to mx. So we're going to solve now, and for x we're going to put L over 2, right? So we're going to say m will be equal to W over 2, and put in L, and for x is L over 2, right? So I'm going to multiply by L over 2 here, and I'm going to subtract from W over 2, and x squared is L over 2 squared, right? And our m bending moment will be equal to with W over 4 for 2 by 2, and for L it will be L squared. And we are going to subtract here 2 by 2 by 4, it will be 2 cubed, that is W over 8, and here we've got L squared. So we've got WL squared, WL squared, we're going to factorize here. So the bending moment M will be equal to WL squared and of 1 over 4 minus 1 of 8 here, and it will be equal to, if we subtract here WL squared, we have 1 over 8. Okay, so M, this is M will be equal to WL squared over 8. Okay, so this is how we derive for the bending moment for a simply supported beam with a uniformly distributed load on it. So this is how we calculate it. Let me make it a bit bold. Okay, thank you for watching, and I hope this video is useful to you. Please do not forget to subscribe my channel, leave a comment, and hit that like button as you hit that also the notification bell, so that you don't miss any one of my following videos. In the next videos, I'll be showing how to calculate for the angle of deflection and the deflection also for a different types of beams. Till next time, bye bye.